We're on number 10 now, so let's take a look and go as far as we can here on this 15-minute video. An accountant has observed that 6% of all copies of a particular two-part form have an error in part 1, and 4% have an error in part 2. If the errors occur independently, find the probability that a randomly selected form will be error-free. Okay, now let's remember these errors are independent. And if they're independent, we're allowed to multiply our two events together to get the intersection of this error-free form. All right, so what we really want is the probability that there is no error in part 1, and we're allowed to multiply that times the probability that there's no error in part 2. And we can multiply these two together because they are independent from one another. All right, so the probability that there's not an error in part 1, well, there's a 6% chance that there is an error. So 1 minus 6%, we're going to have 0.94 as our probability. Doing the same thing for the second part, 4%, we have 0.96 as our probability. And then we want to multiply those together to get our final probability. And this ends up giving us 0.902. All right, so let's look at 11. We want to classify each of the following as discrete or continuous. Now remember, if it's discrete, it's a counting number. If it's continuous, we can have decimals in between. So let's look at A, the weight of a dog. Well, we can certainly have a dog that weighs 45.5 pounds. We can have a decimal in there. So this is continuous. Let's look at B, the number of dogs in a kennel. Well, this is a counting number, so this is discrete. The amount of food in pounds that each dog eats. Well, again, we can have a decimal when we're talking about the amount of food in pounds. We could have 3.5 pounds. So since we can have that decimal, this is continuous. All right, so let's look at 12. Determine whether the table is a valid probability distribution of a discrete random variable. All right, so what's important here is first, let's remember discrete means that all of our values of x are counting numbers, which they are here, so that's okay. But there are two things we need to look for when we look at our probabilities here. We're not allowed to have any probabilities that are not between 0 and 1. And let's notice all of these are between 0 and 1, so we're okay there. But the second condition is that when we add up all these probabilities, they should add up to 1. So let's see, this is going to give us 0.4, 0.5, 0.7, 0.8. This does not add up to 1. So this is not valid. It gave me another. Yeah. Okay. Let me go down here. So down below it, it's not valid. The probabilities don't add to 1. All right, so now let's look at 13, and I'll just sort of pull this down to the second page. A discrete random variable x has the following probability distribution. We want to do several things. Compute the probability of x being equal to 3, the probability x is greater than 3, the probability that x is greater than or equal to 3, the mean of x, the variance sigma squared of x, and the standard deviation sigma of x. All right, so let's start with the probability of 3. That's easy enough. If we look over here at 3 and down at its probability, that is 0.1. All right, now probability that x is greater than 3, well, the numbers that are greater than 3 are 4 and 5, so we want to add up 0.4 and 0.2, which makes this 0.6. Now, B and C are different because the probability x is greater than or equal to 3 means we also need to include the 3. Its probability is 0.1. So if we add that to what we already got here, we are going to have 0.7 for this probability. All right, now for D, the mean mu of x. Our formula for the mean is to sum up all of the x times p of x's. So we want to multiply each one of these columns together and add them up. So let's just go ahead and put that out here to the side. So, and instead of going and hunting for my little mu in my symbols, I'm just going to write the word mean. All right, so we're going to do 1 times 0.2 first. That's our first column. 2 times 0.1. 3 times 0.1. 4 times 0.4. And 5 times 0.2. And when we put this whole string of calculations into our calculator, that's going to give us the mean. And that ends up being 3.3. All right, now the variance is a little bit uglier formula than the mean. So our variance, sigma squared. Recall, if you look back at your notes, it's the sum of the x squared px's minus the mean squared. All right, so we need x squared times px, and then we want to add all of those up. So what we're going to do is square this number and multiply times this number here, and then add each one of those up for the first part of this. So if we square 1, we'll get 1 times 0.2. If we square 2, we'll get 4 times our 0.1. If we square 3, we'll get 9 times our 0.1. If we square 4, we'll get 16 times our 0.4. And if we square 5, we'll get 25 times our 0.2. Now, we're going to add all of those up, but we want to subtract off our mean squared. And our mean that we got in part D was 3.3, and we want to square it. So I'm just going to write it like that for now. So we can put all of this in our calculator at once. And we get 2.01. All right, now we've got our variance. Let's now get the standard deviation. Fortunately, that calculation is now easy. Once we've got the variance, the standard deviation is the square root of that number. So the standard deviation is going to be the square root of 2.01. And if I just take it out 3 decimal places, I get 1.418. Okay, now let's look at 14. 6,000 lottery tickets are sold at $2 each. One ticket will win $5,000, one will win $3,000, and 3 will win $1,000. Let X denote the net gain from the purchase of a randomly selected ticket. We're going to first construct the probability distribution of X, then we're going to compute our expected value, or our mean, and then we're going to compute the standard deviation of X. All right, so let's start with part A, our probability distribution. Okay, so I made a table in here for us, and I'm going to call the first column X and the second column its probability. And we're going to list all the possibilities. Okay, so let's say that we are lucky and we win $5,000. Now, the truth is we don't really win $5,000. We win $4,998 because we spent $2 on a ticket. So the chance, or let's say that's 4,998 is the outcome, and the chance of that, since there's 6,000 lottery tickets, is 1 out of 6,000. All right, well, let's suppose we win the 3,000. Well, again, we don't really win the 3,000. We win $2 less than that because we did spend $2 on a ticket. So 2,998. And again, there's only one opportunity out of 6,000 for us to win that ticket. And then let's do the same thing for the 3 winners of $1,000. Now, if we win that $1,000 ticket, again, we only get $998 out of the $2 we spent. But Since there are 3 such opportunities, our probability is 3 out of 6,000 to win that ticket. Alright, so now let's consider the other possibility. We don't win at all. Well, what does that mean? We're really out $2. So our net outcome is -2. Alright, and what is the probability that we don't win? Well, let's notice that there's really opportunities of 5 out of 6,000 to win a ticket. So the opposite of that is going to be 5,995 out of 6,000 tickets that do not win. And now that is our distribution. Okay, so now we're going to go on to part B and compute the expected value. Now remember what we did for the mean in number 13. It's the same idea. Expected value is the same thing as the mean in this scenario here. So we're going to do the same thing that we did up here. We're going to multiply the x column by the p of x column and add up each one of them. In this case, of course, I've written it out in the different format than this over here, so we're going to go across instead of down. Alright, so our expected value is going to be equal to 4,998 times 1 over 6,000 and 2,998 times 1 over 6,000 and 998 times 3 over 6,000 and finally, and I can say minus 2 times 5,995 over 6,000. And then we want our calculator to do this calculation for us. Alright, so this ends up being, it comes out negative 0.4993333. I'm just going to go ahead and round that up to 50 cents. Alright, so negative 50 cents. So if we were to take everybody's winnings and everybody's losses, add them together, average them up, on average, there's a loss of 50 cents each. Alright, so part C is compute the standard deviation, and since that is a little bit more complicated, as we saw in part E, I'm going to leave that for another video since I'm down to 2 minutes on this one. And we'll get part C there in the next video.